We are beginning the new chapter 7.1, and 7.1 is actually both on growth and decay functions, but we're just going to focus in on growth functions today, all right? And before we even start talking about growth functions, let's review what we already know, what type of graphs we've already graphed, kind of like parabolas. You guys remember parabolas? You guys remember vertex form on parabolas? If you don't, you're going to not really do well on this section, but I hope you do remember that vertex form HK was your actual vertex. Your A value told you what? If it was positive, what would happen with the parabola? If it's positive, it opens up. If the A value was negative, it opened down. Not only that, like if you were to compare, like let's say y equals, let me say 2x squared compare that to y equals 1/2 x squared. Well, both of these open up because they both have the A value that's positive, right? But the HK, they're both 0, 0. So you could actually do a quick sketch of these if you wanted to. Both of them opening up. But that A value of 2, you know what that would do? That would cause a vertical stretch. You guys remember that? No. It makes it a little narrower. As opposed to the A value of 1/2, which causes a vertical compression, which makes it a little wider. I hope you guys remember that. And if we did have an H and K, like let's say that it didn't have an H with X, but let's say you had a K like a -3 on this one right here, a -3 on that one, that would cause this whole wide parabola to shift down 3 units. So it'd be like 1, 2, 3, and your parabola would be down here instead of up there. Do you guys remember that stuff? Please tell me you do. Yes? Okay. So vertex form, the A value tells you if it opened up or down. Told you if it was wide or narrow. The HK causes a shift. And the most recent type of graph that we had was square root functions. Y equals A times the square root of X minus H plus K. Again, the A value, if it's positive, it opens up. If it's negative, it opens down. If it's a bigger number, it gets vertically stretched. If it's a number closer to 0, it gets vertically compressed. Same concepts. We're going to be using all this information in terms of A, H, and K on today's exponential growth functions. So before even beginning the lesson on exponential growth functions, let me give you a real life example of an exponential growth function. Here it is. All right, let's say a mysterious man comes up to you on the last day of school and says, I need you to wash cars every single day for 30 days straight during the summer. I'll pay you good money. You ask him how much. He responds, whatever you want. You say $1 million. He stops and thinks and says, sure, I can give you the million, but how about instead of $1 million, I give you a penny right now? The first day of work, I'll double it and give you 2 cents. The second day of work, I'll double it and give you 4 cents. Each day, I'll keep doubling the previous day for 30 days straight. What do you say? How about this? I want to pause it now, talk to a partner, and just to make sure you really understand, look, you're talking to this guy, and he just gives you 1 penny for talking to him. And then on the first day of work, you work from morning to afternoon, you only get paid 2 cents for that first day of work. The second day, you only get paid 4 cents. And the third day, only 8 cents, and so on and so on. So look, the fourth day, you get paid 16 cents, and so on and so on. Talk to a partner. How many of us say you'd rather have the $1 million up front? Okay, there's a large amount of us. How many of us say that you'd like to take that 1 cent and then double it? Okay, a couple of, or a significant amount of you too. All right, so it looks about half and half. Check it out. I actually did all the work for you. 1 cent doubles to 2 cents, doubles to 4, doubles to 8, doubles to 16, doubles to 32 to 64. Ladies and gentlemen, if you pick the penny situation, doubling, on the 7th day of work, you work the full day from morning to night only for $1.28. But day 8, it goes up to $2, and then $5, and then $10, doubling to 20, doubling to 40, doubling to 81. On the 14th day of work, now remember, you're only going for 30. On the 14th day of work, you make $163 for that one day. You guys still want the doubling penny? Or you guys want to go for the million? No. Keep doubling. All right, we only have 15 more days to double, right? Let's see what happens. Doubles 327, doubles 655, doubles 1,300, doubles. By day 20, you make $10,000, $10,485.76 on that one day of work. Now, mind you, day 20, $10,000 is not much compared to $1 million. But let's keep doubling for the last 10 days. Doubles to 20,000, doubles to 41,000, to 83,000, 167. You're at over $500,000. You're over $1 million on the 27th day. So just on the 27th day, you're making over $1 million. Then you double it and double it and double it. On the 30th day, you make almost $11 million just on that 30th day alone. And you still have to go back and add all the other ones, right, to see how much you actually made total. This is a great example of an exponential growth function. Now, what do I mean by that? At the beginning, it's like 1 cent, 2 cent, 4 cent, 8 cent. That's lame. That's nothing. It seems like it's not growing at all. But once you get later on down that function, it gets huge, right? It gets huge really fast. That's where the phrase comes from. It's growing exponentially. What does that mean? Like super fast. It's growing like faster and faster each time. Bless you. So anyways, let's jump to our actual handout. Ladies and gentlemen, we are talking about exponential growth functions. A basic exponential growth function has the form y equals a times the base, whatever that may be, to the power of x. Okay. Now we will have an h and a k. The h is always being subtracted from x, and the k is always added or subtracted at the very end. But for right now, we're going to deal with graphs that don't have a h or k shift. So we're just going to be looking at y equals a times b to the x power. This is called an exponential growth function. And similar to the vertex form, y equals, let me actually write that down, the vertex form y equals a parentheses x minus h squared plus k. Similar to that, the a value tells you if it opens up or down. This a value tells you if it opens up or down. The b is going to be the base, which is actually going to be called later on the growth factor. Okay, so we might as well jot down some notes. We could put b is the growth factor. This b. So let's look at this simplest type of exponential growth function. The simplest type of exponential growth function is y equals 2 to the x power. And this is actually kind of like that doubling the penny situation. That's what this does. It grows exponentially. So let's graph this function not using a graphing calculator, but an input-output table, the way we usually do, to get a real good understanding of these exponential growth and decay functions. So I highly recommend that when you graph these, you use consecutive integer inputs. What do I mean by that? A nice number 0, 1, 2, 3, 4, and also go backwards, -1, -2, -3, -4. Always use consecutive integer inputs. It'll make your life a lot easier when it comes to graphing exponential growth or decay functions. In other words, don't just randomly plug in a 1 and then a 5 and then a 7. Don't do that. Let's go nice and in order numerically. When it's in numeric order, you're going to be able to use patterns on the outputs. But let's not use a pattern right now. Let's just plug in 0 right there. What's 2 to the 0 power? 0. Anything to the 0 power is 1. Okay, so 0, 1 is a coordinate. What if I were to plug in a 1 right here? What's 2 to the 1? That's 2. Okay, what if I were to plug in a 2 right here? What's 2 squared? 4. What if I were to plug in a 3 right here? What's 2 to the 3rd? 8, right? 2 times 2 times 2 is 8. Okay, and how about plugging in a 4? What's 2 times 2 times 2 times 2? 16. Now, notice it took me a while to think 2 times 2 times 2 times 2. It's easier to use the growth factor to find your other outputs, right? If you have consecutive integer inputs, if they're organized in numeric order, you could plug in a number, plug in 0, you get out the output 1, and from this single output, you could use the growth factor. What's the growth factor here? 2, to get to the next outputs. So 1, to get to the next one, I want to go times the growth factor 2. 1 times 2 is 2. times 2 is 4, times 2 is 8, times 2 is 16. So it's a lot easier to use consecutive integer inputs and then use the growth factor to get your other outputs. Really easy to do, right? From here, you're multiplying by 2, times 2, times 2, times 2. Backwards, it's not multiplying by 2. It's actually going backwards would be dividing by 2 or multiplying by half. You guys understand that, right? So let's look at these outputs backwards. 16 times half is 8, times half is 4, times half is 2, times half is 1, times half is what? 1/2. Times half is what? 1/4. Times half is what? 1/8. Times half is what? 1/16. Now that's a lot easier than actually plugging in. Imagine if I were to plug in a -1. Well, that would be, okay, 2 to the -1. I have to use rules of negative exponents where you grab it, you move it to the other side, which means you'd have 2 to the 1 down here. You'd have nothing up on top. Oh, that becomes 1/2. See, that's a lot longer to think about. Like you could have, if you wanted to, plugged in -1 and gotten out 1/2. But it's easier to use the growth factor, growing this way and backwards, multiplying by the reciprocal, which would be 1/2. Are you with me? I could have, if I wanted to, plugged in -4 right there and done a bunch of work. I could have said 2 to the -4. What do I do with that? I move it to the other side. It becomes 1 over 2 to the 4. What's 1 over 2 to the 4? 2 to the 4 is really 2 times 2 times 2, which is 16. 1/16 is my answer. A lot faster to just multiply by half and get that 1/16 that way. All right, so let's graph these guys and see what this exponential growth function looks like. 0, 1 is right here. No, it's not. Sorry. Right there. 0, 1 is right there. 1, 2 is right here. 3, 8 is, wait a minute, 2, 4. 2, 1, 2, 3, 4 is right there, and 3, 8 is up here. Now let's go in the negative input direction, -1 and half. So -1 on the x and only halfway up. Okay, only halfway up would be right here. Everybody please put a dot at -1 and then halfway up. And then the next coordinate, ladies and gentlemen, is -2 and then +1/4, which is really half of the half, right? If you think about the growth factor, going this way, it's growing by 2. Going backwards, it's multiplying by half. So it's like half of 2 is 1, half of 1 is half of half is 1/4, half of 4th is 1/8. So you keep getting smaller by half. So this next one is going to be -2 and 1/4. So -2 and only 1/4 of the way up, which is really only half of the half, which would be right about right there. And then the next one, -3 and 1/8, that's only half of 1/4, which is even closer to the x-axis. And the next one, -4 and 1/16, that's even closer to the x-axis. But it's hard for me to draw the difference of of 1/8 and 1/16. It's hard. But we know that if we kept going, like -5, you'd get 1 over 32. And -6, you'd get 1 over 64. So we know that as you, whoa, that did not work out the way I wanted it to. What happened? No manches. Okay, sorry about that. But what I'm saying is, as you go this way, it'll infinitely get closer to the x-axis, but never actually touches the x-axis from right to left. Does that make sense? Or does that seem weird? Seems weird, huh? Let me demonstrate what we call an asymptote. By the way, the x-axis in this case, this is called an asymptote. So let me actually jot that down for you. Asymptote. Asymptote. Okay? What does that mean? That this graph from right to left will infinitely approach but never actually touch. Let me demonstrate it in the real world here. Okay, so I'm gonna watch my feet. Okay, got my feet? Oh, kind of, you gotta get closer. All right, so I'm gonna take 4 steps towards that wall. Okay, 1, 2, 3, follow me, 4. Okay, I traveled 4 steps, right? Get over here. Okay, so I'm gonna go now half of that distance, 2 steps. 1, 2. Now I'm gonna go half of that distance, 1 step, 1 step. Now I'm going to go half of that distance, which is half a step. There's half a step. And then half of that, which is half of the half, and then half of the half, and then half of the half. Next thing you know, I'm doing this. I will never get to that wall. Does that make sense? Because you keep traveling a smaller and smaller distance. So you'll never get to the wall. That's an example of an asymptote. You're never going to get there. You could pause it now. Okay. Dude. Hey, it's still recording. What's up, guys? Dude, no, I don't want to be on YouTube. Anyway, I hope we understand what an asymptote is. Your graph will infinitely approach but never actually touch. So here's my graph. And when you draw it, you could draw it like if it's actually touching, even though if somebody asks you, does it actually touch? No, it never actually touches. It infinitely approaches but never touches. So this is what we call an exponential growth function, okay? And how could we be clear of what an exponential growth function is? From left to right, it kind of seems like it's not growing at all right here. It's like saying 1 cent, 2 cent, 4 cent. That's nothing. But then when you're talking 10,000, 20,000, 40,000, that grows exponentially, right? Exponential growth function. So from left to right, your exponential growth function will grow away from the asymptote. It is possible to have a positive exponential growth or a negative exponential growth. As long as it's growing away from the asymptote, it's a growth from left to right, okay? So an example in the real world, besides me stepping half a step closer to the wall, would be like saving money, right? If you save a penny, then you double it and double it. At some point, you're going to have a lot of money, a ridiculous amount of money, right? If you keep doubling it. Or how about an example of exponential growth in a negative direction? Let's say you have a bunch of credit cards, but you don't use them. How much do you owe? Nothing, right? If you don't use them. But then you start using them and start using them more and more and more and more, it's going to grow in a negative direction. That's a growth in a negative direction. So exponential growth, it could be positive, opening up. It could be negative, opening down. You guys agree with that? Or do you guys understand that? Okay, what do you think when we get to this point? Y equals a times b to the x minus h power plus k. What value do you think will tell you if it opens up or down? The a value. Just like on vertex form, the a value tells you if it opens up or down. Okay. The b value is the growth factor, and that's what actually tells you if it grows or decays. But on this first page, on this first part of the notes, we're just focusing on growth. And growth, it could be from left to right, growing away from the asymptote in a positive direction, or from left to right, growing away from the asymptote in a negative direction. That's still growth, even though it's growing in a negative direction. All right, so let's actually take a look at this guy right here, and let's make an XY table for it, and let's graph it. But before we actually graph this guy, let me show you what I need to see, or what I recommend for you to do, is to write it as y equals -1 times 2 to the x. You see, your base is not -2. Why not? Why is the base not -2? Because there's no parentheses around that thing, right? There is no parentheses around that thing. So it's really 2 to the x with a negative sign in front. So that negative sign in front is really like the a value of -1. It's going to open down, but the growth factor is still 2, all right? It's still going to be a growth function. So if we were to make an XY table for this guy, plug in 0. If I were to plug in 0 right there, 2 to the 0 is what? Anything to the 0 power is what? 1. And then 1 times -1? -1. Let's use consecutive integer inputs. 0, 1, 2, 3, 4. Backwards, -1, -2, -3, -4. I do this because now I could use the growth factor or the decay factor. What's the growth factor? 2. 2 is the growth factor. That means that the -1 is going to grow by 2, right? So what's -1 times 2? -2 times 2 times 2 times 2. See how easy it is to come up with these outputs? Once you understand how it's going to work, that the growth factor could be used to find the other outputs. Let's say you didn't know that. Okay, well, you'd have to actually plug in 4, like for this input 4 to get the output negative 16, you have to plug in 4 right in there. And you'd have to say, okay, 2 to the 4th power, that's really 16. And then 16 times negative 1 gives me negative 16. It's a lot faster to just do the simple input 0, get the output, whatever it may be, and then multiply that output by the growth factor, which is 2, to get all of the other outputs quickly. And if you could get these outputs quickly by multiplying by 2, backwards it's not multiplying by 2. What is it doing backwards? Dividing by 2. Or multiplying by half, right? Which is the same thing as dividing by 2. So if I go negative 16 times half, it's negative 8. Times half is negative 4. Times half is negative 2. Times half is negative 1. Look how easy the rest of these outputs will be. What's negative 1 times half? Negative 1/4. I'm sorry, negative 1/2. Woo. And then negative half times half? Negative 1/4. Negative 1/4 times half? Negative 1/8. Negative 1/8 times half? Okay, and we know that it's going to keep getting closer and closer to nothing, right? So let's graph 0, negative 1. 0, negative 1 is right there. Let's graph 1, negative 2 right there. Let's graph 2, negative 4. 1, 2, negative 4 is right there. 3, negative 8. Need to zoom out a bit. Oh, no, not again. Hold on a second. Here we go. So negative 3, negative 8, negative 1, or positive 3, negative 8, 1, 2, 3, negative 8's down here. Now let's go in the negative direction. The negative 1, negative half. Negative 1 on the x, negative half on the y. It's right there, halfway down to negative 1. And then negative 2 on the x, negative 1/4. That's half of the half, and then half of that half, and then half of that half. And you could draw dots like if it's actually on there, but we know it never actually touches, just infinitely approaches. So this is my graph. When you graph it, it looks like it's on the x-axis, even though it doesn't ever actually touch it. And it grows in a negative direction. What do you think? All right, so we did mention that the asymptote is the line that it will infinitely approach but never actually touch. So the asymptote here happens to be this line right here, the x-axis itself. That's the asymptote. Let's actually jump over here, guys. Check this out. This is ultimately what we want to get to, and this video is already getting long, so let me jump to this one. Y equals a times the base, whatever it may be, to the power of x minus h plus k. Now, h and k tells you the translation, which means the shift. The h value will tell you how it moves from left to right, and you got to think opposite of whatever you see here because there's a minus sign there. The k value is your shift up and down, and you take whatever value you have right there. So it's going to be a shift 3 down at the very end of it all. But that's your h and k shift. The asymptote, here's a very important fact, guys. I would highlight this if you have a highlighter. The line y equals k will be the asymptote. The line your graph will infinitely approach but never actually touch. Okay? So just by looking at this graph right here, identifying the k value, I know my asymptote is going to be where? What's my asymptote? It says y equals k. What is my y equals k value? What's my k value? Negative 3. Thank you very much. Y equals negative 3 is the asymptote. So on my end product, on my end graph, it's going to have an asymptote at negative 3 right here. Y equals negative 3 is my asymptote, abbreviating. Okay? But right now, we're not even going to worry about that asymptote. Let's graph this guy the way we would graph a square root function or a parabola. How do we graph these type of functions when they were in the square root function or the parabola? You identify h and k, right? What's my h value? H is always being subtracted from x. And whatever you see there, you have to think opposite. So what is your h value? Guys, yes. H is always being subtracted from x, right? It says x minus 1 is a power right here. So your h value, think opposite of what you see here. It's actually positive 1. What's your k value? The k value is negative 3. H value is positive 1. Okay. Now, what would we do after we would identify h and k on square root functions? We would ignore h and k and box in this part of the function. You guys remember that? So we go to an xy table on that boxed in function. All right. Let's do that. Input-output table on that boxed in function. What would be an easy input to plug in? 0. When we plug in 0, check it out. What's 2 to the 0 power? 1. What is 1 times 4? 4. So when you plug in 0, you get out of 4, right? Now, how about this? Instead of plugging in a negative 1 right here, having to move it down and then reducing the fraction, or instead of plugging in a 1 and then multiplying and then plugging in a 2 and then multiplying, instead of doing all that, let's use consecutive integer inputs. 0, 1, 2, 3, 4. Backwards, negative 1, negative 2, negative 3, negative 4. When you have consecutive integer inputs, you could now use the growth factor to grow from one output to the next. So what's this next output going to be based on this growth factor of 2? 8, that's right. So 8 and then 16 and then 32. Now these are pointless because you're not even going to use these guys. Those are already off the graph, right? But it's still good to do because you know it's growing by 2. Backwards, you'd be growing or decreasing by what? Decaying by 2. So instead of multiplying by 2, you're either dividing by 2 or multiplying by the reciprocal of 2, which is half. 32 times half is 16. Half of 16 is 8. 8 times half is 4. 4 times half? 2. 2 times half? 1 times half? 1/2 times half? And you could keep going 1/8, 1/16, 1/32, 1/64, 1 over 128, right? Infinitely approaching nothing, infinitely approaching 0, decaying. So let's graph these guys. Now remember, these coordinates that we found are to this boxed in graph, not including h and k. So I want to graph these coordinates, and then I'm going to shift 1 to the right and 3 down to get my final product, which will end up on this asymptote of the y equals the k value being negative 3. So let me graph 0, 4. 1, 2, 3, 4 is right there. Let me go 1, 8. That's up here. And let me go 2, 16 is already off the graph. Negative 1 and 2. Negative 1 and 2 is right there. Negative 2 and 1 is right there. Negative 3 and 1/2 is right there. Negative 4 and 1/4 is right there. Negative 5 and 1/8 is right there. 1/16, 1/32, 1 over 64, 1 over 128. It's infinitely approaching the asymptote of 0. If the k value were 0, this is what my final product would be. But we know that we need to shift it 1 to the right and 3 down on every single one of these coordinates. So if I go 1 to the right and 1, 2, 3 down, I end up right there, moving 1 to the right and 3 down. Let's move all of them 1 to the right and 3 down. So 1 to the right, 1, 2, 3 down is right there, 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 and it keeps getting closer, infinitely closer to the actual asymptote, which is at y equals negative 3. So the graph with my red dots is my final exponential growth function. Now, let's say you accidentally drew this one, the one that was boxed in. Let's say you accidentally drew it on your test or quiz. Please put a couple of X's on there so I know that that's not the end product graph. It's the other one that got shifted. Are you with me? Okay, now, there's a lot more to learn, a lot more to talk about. Stuff that we already know. But like, for example, this end product exponential growth function, first of all, how do I know it's a growth? Because from left to right, it grows away from the asymptote y equals negative 3. It could also grow in a negative direction away from the asymptote y equals negative 3, but right here it's growing in a positive direction, which also tells me that the a value is positive, which we already knew that. But anyway, let's talk about stuff that we already know, or hopefully we know. If you take a look at that end product graph, as x approaches negative infinity, what does that mean as x approaches negative infinity? I'm telling you to look at this graph in a certain way. Which way am I telling you to look at it? To the left, to the right, up, down? What am I telling you to look at? to the left. As x approaches, x is right here. As you go to the left, what happens to your y values? As x approaches negative infinity, y approaches, or you could say f of x approaches, what does it approach? Positive infinity? Well, that you're saying that as I look at it to the left, it's going to go to positive infinity on the y's?
Approaches -3.
It approaches -3. Think about this, guys, and I don't expect you guys to know this already. Good job, Nathan. I don't expect you guys to know this already, but let me ask you this. What y value are we at right here? That's the y value of like 6, whatever, and then it drops to 1, and then it drops to -1, and then -2, and then -2.5, and so on and so on, and it keeps getting closer and closer and closer to what y value? -3. So as your x go to negative infinity, as you go to the left on this graph, what are your y values doing? They're approaching the y value of 3. Make sense? And we could also say as x approaches positive infinity, where do your y's approach? If you're looking at it to the right, where are your y values going? Well, your y values were at -2 right here, at -1, at 1, at 8, at 16, at 32, at 64. Where are they going? To positive infinity. Okay? So all this notation we're going to have to get really good at some point. Might as well throw it out at you now on this tremendously long video. What else could we talk about this graph? Let's talk about the old school domain and range. Your domain are your x values, right? Does this graph go to the left forever? Yeah, it does. Does it go to the right forever? Yes, it does. Even though it curves up, this graph does exist at negative or at +4. It exists at 332, even though it's not shown here. It exists at +4, 64, at +5, 128. So this graph, even though it goes up, it continues to go this way forever. So the domain is what? X equals all real numbers. It does go to the left forever. It does go to the right forever. Now the range are your y values. Exactly. This graph, is it up and down forever? No, it goes up forever. But does it go down forever? No, it actually infinitely approaches that 3, but it never goes below 3. It never actually touches 3. So where is this graph at? It's above 3. Now you can't put or equal to. That would be incorrect. It's just y is above -3. I said 3, -3, I'm sorry. Because this whole graph is above the y value of -3. What do you guys think? All right. So if we were to go to these guys, like let's say I wanted to, let's graph this one right here. Is there a h or k? No. Let's say I told you, what's your asymptote going to be? It's y equals the k value, right? What's the k value of this guy? 0. So we know that your asymptote is going to be at y equals 0, which is the x-axis. Your graph will eventually infinitely approach that asymptote, never actually touch, just infinitely approach. Let's say I wanted to get an xy table going, which we do. What input should I put in? 0 is the easiest? Sure, you could put in any one you want. And what should I do with the other inputs? Consecutive integer inputs. Nice and in order. 0, 1, 2, 3, 4, backwards, -1, -2, -3, -4. Plugging in 0, plugging it in right here. What's 4 to the 0? 1. What's 1 times half? Is 1/2, right? 1 times half is 1/2. Now, I could, if I wanted to, plug in a -3 and get 4 to the -3rd power, which means I have to move it down and I have a fraction divided by a huge number. It gets really complicated doing the math. So it's a lot easier to use the growth factor to get from one output to the next consecutive output. So what's my growth factor? In other words, what's this going to grow by? Come on, guys, I have a dot right there. What's it going to grow by? 4. That's the growth factor. The base is the growth factor, okay? It's going to grow by 4. So if I have 1/2 and I make it grow by 4, what's 1/2 times 4? 2. And then 2 times 4, 8. And then 8 times 4, 32. I'm already off the graph. I don't have to do anymore. So if this way was multiplying by the growth factor 4, backwards would be multiplying by the reciprocal of 4, which is 1/4. 32 times 1/4 is 8. 8 times 1/4 is 2. 2 times 1/4 is 1/2. 1/2 times 1/4 is 1/8. 1/8 times 1/4 is 1/32. Now at this point, it's not really important of being that accurate because you know it's approaching 0. 1/32 is hardly anything. Michelle, what do you think? You got this? All right, so let's graph the 0 and the 1/2. 0 on the x, 1/2 on the y is going to be right there. And then go to 1, 2, and then go to 2, 8. And let's go to -1 and 1/8. -1 on the x and 1/8 of the way up. That's not even halfway up. It's not even half of the half. It's really, really close to nothing, 1/8. And we know that the next one, 1/32, is even closer to 0, but you can't really draw the difference there. You could just draw a bunch of dots like if they were touching, but you need to know that they're not actually touching. They're just infinitely approaching. So here's your end product graph. Why do I say it's the end product? Because there is no h or k to shift. So this arrow better be straight because it never goes down below that asymptote of y equals 0. Okay. Any questions? All right. Well, you guys could try the other ones, and that'll be the assignment for today, just to finish it up. Or at the very least, watch this video over again so you get a better understanding for tomorrow. We're going to continue with the same exact lesson, but decay functions instead of growth functions. You know what? I might as well give you a little taste of that right now. Check it out. What determines if it's a growth or a decay function? The growth or the decay factor, the b value, okay? If this b value is greater than 1, it's going to be a growth function. From left to right, it will grow away from your asymptote. If your b value is a value that's closer to 0, less than 1, closer to 0, it's going to be a decay function. From left to right, it's going to decay towards your asymptote, okay? So a growth function, something bigger than 1. A decay function, a fraction that's less than 1. Okay, and that makes total sense because if I take any number like 10 and multiply it by 1.5, it's going to grow. If I take 10 and multiply it by 2, it's going to grow. If I take 10 and multiply it by any value greater than 1, it's going to grow. But if I take 10 and multiply it by a fraction less than 1, it's actually going to decay. It's going to shrink. Okay, so the b tells you if it's a growth or decay. If it's a value greater than 1, it's going to grow. From left to right, it's going to grow away from your asymptote. Just like right here, from left to right, it's growing away from the asymptote. Even if it's negative, it's going to grow away from the asymptote. But a decay function, as we're going to see tomorrow, it's going to start way up here, and it's going to decay down to the asymptote. If your b value is like the fraction 1/2, it's going to decay down to the asymptote. Or it might be down here in the negatives and decay down to the asymptote, right? If your b value is a fraction that's less than 1. Yeah, watch this video again. Hopefully it helps. Gets you ready for tomorrow.